Today we're going to look at the mechanical end of an electronics design project inside SolidWorks. Now we have three main requirements. First, we have to get and send data to our IC designer. Then I need to validate that this design will stand up to the rigorous vibration environment it'll see in the field. And finally, we're going to make sure the enclosure design allows adequate cooling of all the electrical components so they're within spec. So let's get started with IC design. Now, working with the IC designer means I need to bring in PCB data before the designs are necessarily complete. This way I can inspect it and build my model around it. I also want to see how it's going to respond using my simulation tools. So I need a tool that lets me bring in ECAD data as well as communicate it back to the electrical engineer if I need to make a change. So this has historically been a really big time sink when we're trying to make 3D representations from electrical models. But you can see here in SolidWorks that SolidWorks streamlines this data transfer. It allows me to not only bring in and build the models, but it's referencing an already built component library. So you can see here all the different chips, transistors, and resistors. Now I'm going to go ahead and filter my feature design tree here and just pick all these large circuits. Notice I'm using configurations to reference already simplified versions. Now these simplified versions mean that I can run simulation without having to mesh all the little connections. And since I'm just going to want to run perhaps a quick modal analysis or just get some mass properties or see if it's going to fit in the enclosure, I can go ahead and just skip out on keeping the detailed model and make a quick simplified version for my simulation. So you can see here that very quickly I was able to build the 3D representation of my board. Using configurations, switch to simplified versions, and now I'm ready to do a little bit of simulation. Now for simulation there's a preliminary requirement that the fundamental frequency of this board is above 60 Hertz. So I'm in a modal study here, and you can see that I've restrained with fixtures the four corners where this thing is going to be bolted to the fixture. Now, taking a look at the first or fundamental mode, we see it's a little bit under 30 Hertz, and we can see the deformation, or the mode shape, if you will, if we animate it, and so you can see right where the trouble spot is in this first mode. So we're not meeting this requirement of the fundamental frequency being above 60 Hertz. So looking at that mode shape, though, we can suggest a simple change of just maybe adding an extra mounting hole towards the center of the board. So what we'll do is just go ahead and edit this thing in context, and we'll use some of the SolidWorks tools to quickly make a hole. Now here's where the big roadblock would typically be, right? How do we communicate this change back to our electrical engineers? We're going to actually drill a hole in the board, which means that copper traces are going to probably have to move, other chips are going to have to maybe move. So it's imperative that you have a tool such as SolidWorks, which allows bidirectional communication. So we'll go ahead and just make a sketch, make some sketch constraints, and turn this thing into a hole. Now, also while I'm doing this, I'm kind of looking at the clearances, and I notice a few components over towards the left-hand side are kind of close to the chips. So I know that was a problem last time with my thermal design, so I'm just going to go ahead and move those right now. So the important thing to note is I need to communicate this back, right? I go to SolidWorks, and I just tell the software, export this to SolidWorks. And what you see is that it quickly updates the ECAD file, and then I can send this out to my ECAD designer in an IDF or IDX ProStep EMD format. Thus, I'm able to complete the loop, and the electrical designer is apprised of my change right away and can start modifying his circuit design. So what do we see? We saw using SolidWorks and simulation in SolidWorks let me collaborate with electrical engineering and let them know there might be a problem before it's much later in the design process. Let's talk about vibration testing, right? There's maximum acceleration, stress, and displacement criteria for my components, so let's see if our board is going to stand up given that new mounting hole. So going into simulation, we're going to start off again with the modal analysis. Now modal is going to show us two things: the frequency at which we're going to have resonance, and then the mode shape. But it doesn't give us the full piece of information of displacement, accelerations, and stresses. So we'll start off and again just verify that that center mounting hole rectified the problem of the fundamental frequency being a little bit too low. And we can see here that that hole has indeed shifted from about 30 to 70, the first frequency. So visualizing the mode shape here in an animation, this helps me to qualitatively identify problematic areas. So we can see the shapes, and we can see where the maximum displacement is going to be in response. So we can see if there's going to be sensitive components that are going to be subjected to resonance at various frequencies. Here we're looking at the second mode, and of course we have a different shape here, right? Different areas of the board are going to be in resonance at this frequency of about 99 hertz. So this is very valuable information to identify what frequencies I might have issues at, and then where on the board I might have issues. And we can look at a few of the higher mode shapes. But what this really isn't telling me is two things that I know I'm constrained by in this design. Stress of the board, we're going to allow for about 4,000 psi, but also acceleration, right? A lot of these sensitive electronic components have maximum acceleration components, that typically we test in the field with accelerometers. So let's move into some more dynamic studies and get what we call the response. So we've met the frequency requirements. I'm going to go into a harmonic response. Now what we're looking at here is basically a sweep test. We're going from 0 to 120 hertz. That's my sweep frequency. And then what I'm going to excite this with is basically a 5G load in the out of plane direction here. So you can see the arrow and you can see the 5G magnitude. And that's just consistent across the 0 to 120 hertz spectrum. So now we're solving and we're actually going to be able to get the response. Now, you can imagine in the physical lab we'd have a shaker table test, right? And it's not going to give us this kind of information, though. I've isolated the board. I'm looking at stress of the board, maximum stress, and it meets my requirements of 4,000. And it also meets my displacement requirements of about 50,000. And that's even at resonance across the entire spectrum. Looking at all the components, we can look at acceleration. And the critical components that I might put an accelerometer on, I can look at acceleration versus frequency, right? And so we can see the response throughout the entire shaker table test. Additionally, we see maybe a more problematic area. We can take our probe command, just like a little sensor or accelerometer, and we can see that different areas of the board, of course, respond differently at different frequencies. So it's a very multidimensional problem, but all this information I can quickly pull out from the simulation. So what did we just do? We saw that simulation allowed us to test for things like acceleration and stress and displacement without having to go and make a physical prototype and outfit it with accelerometers and strain gauges. So we can validate our design up front before we go to that part. So let's go into cooling design, and I need to make sure that I have adequate airflow, vents, and fans so my chips don't overheat. So what I have here is the entire enclosure for my rack-mounted unit here, and you can see that it has some active cooling components on the back, such as two axial fans. I also have some vents on the side. So one of the things I want to do is just quickly evaluate, is this going to be adequate airflow to cool my design? Now, to make things a little more interesting, we have a little design challenge here for you. We have 3 different options for the top lid. So this is option A. We can call this the ring approach. We also have this one, just a more conventional pattern of slots. And then finally we have no lid. So one of the cool things about simulation is being able to test, any concept we come up with and see how that's going to affect things like thermal performance. So I need to run a thermal fluid problem. I'm going to hide the top lid just so we can see all the insides of this. And I'm going to flip right over to flow simulation. Now, again, since I'm staying inside of SolidWorks when it comes time to doing things like bringing in material properties, of course, all those properties are already there, right? Because remember, we started with the CircuitWorks library of SolidWorks parts that had configurations and material properties. We designed in SolidWorks, so all that stuff is maintained. And, of course, I bring it into flow. I have a couple pressure conditions, and all I'm doing here is just applying what we call pressure condition, but you really apply what you know in flow, whether it's a flow rate, if I had a nozzle or something, or a pressure. So I'm just telling the software, hey, I have ambient pressure where these vents are open to the outside air. But of course, I could do things like modify the temperature if I wanted to modify those boundary conditions. Now, I can also take a look at fans. And if you think of fans, they, of course, are going to induce flow, but they don't do it in a steady state way. So in my engineering database, I have what we call fan curves. And of course, you can get these from manufacturers, or else we have a very good representation in our library. And the fan curve is just going to give us a different flow rate based on the pressure differential. So being able to simulate a fan inside Flow means that I don't have to actually model rotating blades and solve for that problem when that's already published information from our supplier. So in the engineering database, you can see we have all sorts of stuff from resistor components all the way down to contact types. You can see I have 3 fans in my system, but I also have heat sources, and of course these are going to be the culprits when it comes time to having to cool this thing down. So I'm applying various wattages, we call these volume sources, and then finally I'm using what I call a 2-resistor component to define a little bit more complex interaction between a board, junction, and a case. And it lets me really just simplify and get the behavior of a chip without modeling the entire connectivity and resistance of the board. Now, PCB is an interesting animal because a PCB is a very anisotropic material. So what I can do here is put in things like percent copper or mass of the board along with the thickness of the board. And what it's going to do for me is figure out what the bulk thermal properties are without me having to know them prior to running the analysis. So it can figure out for me based on a few physical parameters of the board. So that's a PCB model and allows me to simply represent the behavior, again, of a more complex piece. I want to know the maximum temperatures of the PC board, the LCD display, as well as the sensitive chips. And since we have multiple electrical components, we can set up a goal to monitor temperatures or other parameters of each one of these so I can monitor it while I'm solving and also get a streamlined report when I get my results. So taking a look at results, what are we really interested in? Well, temperature is obviously going to be a big one. We want to look at the temperature of the fluid, the air in this system, but also the solid components. So what I'm looking at here are what we call cut plots, and they let me basically make a plane and color that with temperature. So here we have 40 degrees Celsius being the maximum temperature, making the model a little bit transparent or maybe hiding a few components, and now we can really see the situation that's developing within my enclosure. Can run that cut plot through the model, and this is a lot like that modal analysis we did earlier. Real quick pass to show me, hey, this might be a problem area where I have a big blotch of red, in this case temperature. Now let's also take a look at how effective these fans are working, and I'm going to make some cut plots with velocity. So we have red to blue, again that's speed of the airflow. Blue, there's no airflow. Red, there's a lot of airflow. And the arrows are showing me exactly the direction that the flow is going, so I can see if we're not really capturing flow where we need it. So looking a little more detailed, let's look at the PCB board and the temperature plot. And again, if 55 degrees, for example, is our design limit, we can see that there's some areas on the board that are pretty much going to fail when we get to a field test and we start putting thermocouples on the board. We can see here the chip components, again the ones in the back, they're not getting cooled very well. So what's going on? Flow trajectories let us show in 3D those same streamlines we were just looking at a few seconds ago. And so what we're looking at here is the airflow of the fans to the vents. And if we take a look maybe at some animations and then take a look at a top-down view, what do we see? Well, the airflow is just going right out the side. So even though we have 2 fans and 2 vents, it's pretty much really biased towards the right-hand side. And that's why we're not getting very good cooling over those chips. We're not having a really good airflow. So let's see if we can make this design a little bit more effective. Remember those goals we set up? I can right-click and export those to Excel, and this is going to give me the more quantitative information. And remember my design goal, keep things maybe below 65 degrees C. So we can do that right away, and then go ahead and evaluate these goals with those 3 different design options of the 3 different enclosures. And what do we see? The yellow is actually the winner with no vents. Taking a look at the flow of the configuration with no vents, we see that the no vents is the winner because it allows the flow to go to the right and to the left pretty evenly, and we can see all the flow over those chips for cooling. So I'm able to make sure that I have the best design, again, without going to a wind tunnel or lab testing. So out of those 3 design options, we're able to pick the best one and make sure that any conceptual design that I have, I'm able to evaluate it up front. So we looked at collaborating with electrical engineers, validating physical tests, and choosing the best design alternative. But what does this really mean to me? It means that if we can ask the right questions to SolidWorks, we'll be able to get the answers that drive best designs.